session. Below the megahertz, we will have two speakers, and so the first would be Masha Baryakhtar. I hope I pronunciate it properly. She's from Washington University, and you have 25 minutes, and then I tell you when there are 5 minutes left, and we have 5 minutes for questions as well. Go ahead.
Hello. Thanks for having me. Can everyone see my screen? My slides?
Yes.
Okay. I might not be able to see the comments, but I think the questions are at the end anyway. Anyway, so thanks for inviting me to this very exciting workshop. Unfortunately, due to time zone differences, I'm not going to make much of it, but it's still nice to be here. So I'll tell you about searching for new beyond the standard model particles, in particular axions, using gravitational waves, and specifically high frequency gravitational waves. To start off, I just want to put all the scales in context, since we're sort of switching gears from the morning sessions. What we'll be talking about is very light bosonic particles on whose wavelength is of the order of the size of astrophysical black holes. And we'll see that black holes in our universe will provide basically laboratories to search for these light particles, which otherwise we might not be able to see in the laboratory on Earth. And the typical length scales we'll be dealing with is orders of kilometers, tens of kilometers, which are the sizes of astrophysical black holes. Say 3 solar mass black hole, its radius is 10 kilometers approximately. And these will be sensitive to very well motivated particles like the QCD axion for the experts, gut to Planck scale decay constants. And this corresponds to particle wavelengths, Compton wavelengths that are 10 kilometers. So these are very macroscopic, very light particles, and their frequency will be in the kilohertz to hundreds of kilohertz frequency range, and that will set the frequency of the gravitational waves that you can observe. Can you see the pointer or no? Yeah, okay. So first I'll just say a few brief words about motivation for these ultralight axions, and then I'll tell you about the process that makes these interesting signatures possible, which is black hole superradiance, that extracts energy and angular momentum from rotating black holes and puts it into these clouds of ultralight particles bound to the black hole. And importantly, this is not necessarily require these particles to already be out there as dark matter or just background density. This can happen for any particles that exist in the Lagrangian of our universe. And then I'll talk about gravitational searches for these new particles. So how should you think about the QCD axion or axions in general? I won't go into all the theory motivation here because we don't have so much time, but you can think of them as solutions to these theoretical puzzles of symmetries that we still have in particle physics. So we have the standard model, which describes most of the interactions that we understand, but there's a few parameters that are still puzzling for us. And one of those is called the strong CP problem. And the axion was introduced to resolve this problem in a very elegant way. And these particles have properties that they're approximately massless, and they have a small mass that's generated in inverse proportion to its couplings, which is this high scale FA. And that's the scale from which the axions kind of arise. That's where the symmetry is broken. So we tend to think of this scale as often being connected to other important scales in particle physics, like, for example, the grand unification scale, where there are a lot of other symmetries that start to come about. And so that's the interesting thing, is that you can look for these very, very light particles, but they can be connected to very, very high scale. So in addition to just discovering a new particle, it can teach you something about physics that is otherwise very difficult to reach. And they're also good dark matter candidates. There are a lot of searches for these axions in dark matter experiments, and they're also currently very well constrained in certain parts of parameter space by astrophysical object. And in that line of thought, we'll talk about another class of astrophysical object, which is black holes. And we'll see that they can teach us something about these very light particles. So this is a parameter space of axions. Just to situate you a bit, on the x-axis is the mass in electron volts. On the y-axis is this coupling scale in GeV. So stronger couplings, smaller suppression scale is the top, and weaker couplings is at the bottom. And for reference, I put the QCD axion line, where the QCD axion solves this strong CP problem. But the more broader parameter space is also interesting, for example, for dark matter. And I've pointed here to a particularly motivated corner of this parameter space, which is the QCD axion, where its decay constant corresponds to the grand unification scale, which sets it at frequencies of about hundreds of kilohertz. And as you can see, all of the other constraints that we currently have are shown in gray, which are quite far from this gut scale axion. There's some ideas of how to get there, but it's very, very difficult at the lab. So we need new ideas. In particular, we need these black hole searches. So what is superradiance? It's quite a general process, which says that a wave scattering off of a lossy rotating object can increase in amplitude by extracting its energy and angular momentum. And the growth of the amplitude of the wave is proportional to the probability of absorption onto the object in the rest frame of the object. So this dissipation is actually necessary to break, you can think of it as energy conservation or time invariance in the wave packet, and it can either grow or decay. If the object is rotating fast enough, the amplitude of the wave will grow and you'll slow down the rotation of the object. In this case, we'll think of the object as a black hole. So as I said, this process happens if the superradiance condition is satisfied, which is that the angular velocity of the wave, omega A, is slower than the angular velocity of the black hole horizon. And the angular velocity of the black hole horizon can be quite fast because these can be rotating relativistically. So this is the picture where you have an incoming wave and then it scatters and goes off to infinity with a larger amplitude, but you can also have the case where these are bound waves. That can happen if the wave has a small mass, just like axions do. And if these waves are trapped near the black hole, rather than massless waves scattering to infinity, the black hole can repeat this process continuously. So if the wave has an angular velocity around the black hole, and that velocity is smaller than the black hole rotation, then the wave will get continuously amplified and extracting energy and angular momentum from the rotation. And this will be localized, the wave will be localized around the black hole just by gravity. So we're not assuming any other interactions by this potential, which is G Newton times the mass of the black hole times the mass of the axion, which I'm calling mu, over R. So that's what allows these waves to be bound to the black hole just because the axion has a mass. And for the high rates of this process, you want that the constant wavelength is comparable. So this orange wavelength should be comparable to the black hole radius, so that the bound states are localized close to but outside of the black hole. So we all know how to solve this problem, at least in the approximation where we're far away from the horizon. It's a 1 over R potential, and that reminds us of hydrogen atom in first year quantum mechanics. So we can solve for the energy density of these axion bound states for different quantum numbers, NLM, where N is the principal and L and M are the angular numbers. And so here you can see what the configurations would look like for 0 angular momentum, which doesn't superradiate, or 1 or 2 angular momentum units. And so you have this analogy in mind. I can go through some of the comparisons. So the fine structure constant is just the coefficient of the 1/r potential in hydrogen. So there it's 1/137. Here we have a gravitational constant times the mass of the black hole times the mass of the axion. You can also think about this as the ratio of the black hole radius to the Compton wavelength of the particle. And the radius of these bound states will be proportional to 1 over the coupling, and there'll be a few to a few hundred Schwarzschild radii of the black hole, so it'll be localized outside the black hole. And the important difference from a hydrogen atom where there's electrons, which are fermions, is here the axions or other light particles you might want to look for in this mass range are bosons, and they will grow to very, very high occupation number, even exponentially large occupation number. So there can be as many as 10 to the 75 to 10 to the 80 particles in these bound states around the black hole. And I'll get to where that number comes from. The other important difference is, of course, that these are growing bound states. So unlike hydrogen, where you impose that the wave function is regular at the origin and at infinity, here the boundary conditions at the horizon of the black hole are that everything falls into the black hole because it's a black hole. So that gives you an imaginary frequency in your energy because it's breaking the hermeticity of the problem, and you get exponential growth of particle number as long as the superradiance condition is satisfied. So the energy of each particle is given by its mass minus its binding energy, just like for hydrogen. But now you have this small imaginary part, which is the superradiance rate, that can be positive or negative depending on if the angular phase velocity of the particles in the cloud is smaller than or greater than the angular velocity of the black hole horizon. So how does this look in time evolution? Let's say we have a new black hole that's born in a merger that we've seen in gravitational wave observatories, for example, or in supernova. Say it has a high initial spin. So on the y-axis here is the black hole spin from 0, which is Schwarzschild, to 1, which is extreme Kerr. And on the x-axis is the black hole mass and solar masses. So if you start with, say, a black hole with 0.9 of its maximal spin, and there's a light axion in the theory that has, here I've picked a mass of 6 times 10 to the minus 13 eV, which corresponds to a Planck scale axion. This black hole is rotating fast enough to satisfy the superradiance condition for the L equals 1 axion mode. So the kind of 2p level of axions around the black hole. And it'll superradiate, and the number of axions will grow exponentially fast. And then once you have these large number of axions, they actually carry a non-negligible amount of angular momentum. In particular, here you carry about 10 to the 78 H bars of angular momentum, which is roughly 20% of the total angular momentum of this black hole. So you spin down the black hole fairly significantly, and you can see in the last E-fold of growth, the black hole loses a fraction of its angular momentum. At that point, the superradiance condition, which is satisfied in these blue regions and not satisfied in the white regions, is exactly saturated, so the black hole and the cloud have the same angular velocity, and the growth shuts off. So given that the black hole spins down, we can use existing measurements of black hole spins and masses in data to constrain the existence of these light particles. So for example, for an axion mass of 10 to the minus 11 eV, we can look at black hole spins measured in X-ray binaries. So here I'm showing the data with error bars in these observations, and the blue regions are the regions where if this particle existed, you would have expected the black hole to superradiate and spin down to the bottom of these curves. So these red points are already disfavoring the existence of these of a particle of a mass of 10 to the minus 11 eV. And more recently, we've gotten new observations of black hole masses and spins in LIGO. So because you need some time for superradiance to work, you need measurements of the two initial black holes, like the ones LIGO Virgo observes, that then merge. Those measurements are not as precise, so you need statistics to determine whether the black holes have high or low spin kind of on average. But with very large numbers of black holes, you expect to see this kind of pattern. So the black hole mass and spin will have some distribution, which is set by just the initial properties of how black holes are born, but you'll have a big region where you don't observe any black holes, and there'll be an overdensity on these superradiance lines of the number of black holes that were born up here and then spun down to the end of the superradiance region before they merged. And there has been an analysis that's been already done on the initial data, which can already tell us something about these particles. So here I'm showing the corresponding constraint from the black holes I showed you before. So these are the X-ray binaries. Each of them excludes a range of axion masses. And in addition, not shown here, there's an analysis, as I said on the previous slide, in LIGO Virgo data, where these two black holes, which had initially rapidly spinning black holes, can exclude another factor of about 2 in mass of axions down here. So this is already teaching us something interesting about this axion parameter space. So in addition to having these gravitational wave signatures, we also have these spin down signatures, excuse me, we also have gravitational wave signatures. So as this cloud grows, you have a huge energy density carried by these axions, and there's a time dependence set by the axion mass. So the pressure or energy density of the cloud have fluctuations, monochromatic fluctuations on timescales proportional to twice the mass of the axion. And these will source monochromatic gravitational wave radiation. And you can see it in the evolution of the number of axions in the cloud. Is you have this exponential growth from superradiance, which plateaus, and then on longer time, parametrically longer time scales, the number of axions goes down because you're losing energy to these gravitational waves. So the axions are annihilating and emitting gravitational wave radiation. And on longer time scales, the next level will grow. This one carries more angular momentum, and it's easier for it to satisfy the superradiance condition, so it can spin down the black hole to lower spins. You can see the black hole takes another jump to lower spins at a later time, but the growth is slower because with more angular momentum, there's a larger angular momentum barrier, so the state is localized further from the black hole and it's less good at extracting its energy. So just to summarize quickly, these ultralight axions, when their Compton wavelength is comparable to the black hole size, can form these gravitational atoms bound just by the gravitational interaction between the two masses. And these atoms grow spontaneously when a rapidly rotating black hole is formed. And the number of axions in each bound state increases by extracting the black hole's angular momentum through superradiance, and it can also emit gravitational wave signals. So just to show you how that would look, this is a full numerical GR simulation by Will East that was visualized. So here you see a black hole in the center and a cloud of ultralight particles around it that was formed through superradiance. And you will see that it has this time dependence. So overall, there's some constant energy density, but there's a smaller component which is fluctuating in time and emitting these gravitational waves off to infinity. So what do these signals look like? Here's a black hole with a cloud around it. It's very simple in the source frame of the black hole system. It's just a monochromatic wave at the frequency of twice the axion energy. So here I'm showing the strain as a function of time in the source, in the frame of the black hole. Of course, if we're looking for these waves on Earth, there will be additional effects like Doppler shifts between the black hole and the experiment. So these very week-long signals can last for years to billions of years, as I was showing on some of the previous slides. The cloud is depleted very, very slowly because you start with a large energy density. And for certain mass ranges of axions, we found that depending on what the black hole distribution looks like in our galaxy, you can have event rates up to thousands that can be observed with future gravitational wave observatories in the LIGO Virgo band. So what do these gravitational wave searches look like? It's not the mergers that we first observed. These are called continuous wave searches, and currently they're geared up to look for rotating neutron stars, which have very similar signals, because if they're slightly symmetric, they'll also emit a gravitational wave signal at twice the frequency of their rotation speed. So there's already great limits on this and searches being done, and now these searches are starting to be tailored to axion superradiance signals as well. So let me skip this, but what we found by looking at some kind of mock data is that with current data that's on tape, you could have hoped to observe tens to thousands of events depending on what the axion mass is. So here I'm showing the axion mass from 0.5 to 4 times 10 to minus 12 EV, and the number of detectable signals ranges from a few to a few hundred for some assumptions on black hole mass distributions and black hole spin distributions. There's a strong dependence on the spin distribution because, as I mentioned, the black hole needs to lose angular momentum for these clouds to form, need to be rapidly rotating. So if black holes are always born with very low spins, say spins below 0.3, then you only see these triangle events here, which are just a handful of events at low frequencies. But for more general spin distributions, you can hope for large numbers of events. And it also, of course, depends on whether you have heavy or light black holes, because remember, the axion wavelength has to roughly match the black hole size. So if the black hole is heavier, it's larger, which corresponds to a longer wavelength or lighter axions. So going to lower frequencies, you need more heavy black holes, and going to higher frequencies, you need more light black holes. But also notice something here is that we're rapidly losing sensitivity at high frequencies. And one of the reasons is that the black holes are smaller, which means they have less overall energy and the signals get a bit weaker. But also LIGOs and Virgo are rapidly losing their strain sensitivity at these high frequencies as well. And we're really interested in being able to go above a few times 10 to minus 12. We want to get to 10 to minus 11 or even 10 to the minus 10 electron volts, where there's really well-motivated axion candidates. And so,
sorry, Masha,
yes.
30 seconds. Okay.
Yes, great. This is my last slide. So, so to finish, we did this study with some of the organizers and participants of this workshop to to see what kinds of masses of axions you could reach with higher frequency gravitational wave detection. So if you have a new detector like the levitated sensor detector that was described in this paper, and George presented, I think, earlier today, you could reach axion masses as high as potentially a few times 10 to the minus 10. So here I'm showing the reach for these axions as a function of axion mass and black hole mass, where the shading of the region corresponds to how far away you could see the signals. So the lighter shading is about the galactic center, and the darker shading is even further away from that, covering potentially the whole to the other edge of the galaxy. So if you have these light black holes and you have these new detectors which are being developed, then you could hope to reach these very exciting heavier axions with the same mechanism. So just to finish, so in the presence of ultralight axions or other light particles, black holes spin down, and there's already constraints on axions in this mass range from the fact that we observe high spinning black holes. But to go to higher mass axions above the existing spin down constraints and toward the very exciting grand unification axions, we need to be able to probe radiation from these clouds over a kilohertz and going to hundreds of kilohertz. And so that's a very exciting target for these high frequency gravitational wave ideas. Thank you.
All right, thank you, Masha, for this nice talk. Okay, so we have Eugene who raised the hand. Go ahead.
Hi, Masha. Thanks for the really interesting talk. I have a question about the populating of the angular momentum mode. So you say that you start with L1, then after a while you start to populate L2 and start to populate L3. What happened? I mean, this is just maybe a hypothetical question, right? So we kind of know that bosons like to stick together. So if I give you a system where there are existing L equals to 2 modes, for example, would you more preferentially populate L equals to 2 modes first, or you still want to populate the L equals to 1 mode before you populate the L equals to 2 mode? So if I give you a system with existing angular momentum that already have some bosons hiding inside the L2 mode.
Yeah, that's a good question. You're absolutely right. So there's another issue here, which is that can I go back? Sorry, one sec. So let me go to this figure. So here, for example, so say we already have a bunch of L2 particles here. If you the superradiance rate is proportional indeed to the number of particles that are in the final state. So there's a difference between the L equals 1 mode and L equals 2 mode, and which is about a factor of 1,000,000 or so in rate, as you can see from this figure. But so if you already have, say, 1,000,000 axions and then L equals 2 level, then that could grow a bit faster. The other thing to keep in mind is that once you extract enough angular momentum and go below this line, what happens actually is that these L equals 1 axions are now unstable. They're rotating slower than they're rotating faster, excuse me, than the black hole velocity. So they'll actually start falling back into the black hole. So that's another subtlety that I didn't mention, but you're right that if for some reason there's already a bound state of L equals 2, it might go faster in that direction.
All right, so we have other 2 questions from Fernando and then Nancy.
Okay, well, thank you. Very nice talk. I really enjoyed it. You mentioned at some point that you wanted to push it to 10 to the minus 10 electron volts because there was a well-motivated theoretical reason. Could you comment on
that? Could I comment on the, well, let me comment on both aspects. Yeah, so what I was saying, yes, so right, so if we go back to this figure, so first of all, so there's 2 aspects of what I was saying. First of all, we already have some constraints from the existence of these high spinning black holes. And like I showed in this plot here, for the QCD axion line, that goes up to roughly 10 to the minus 11 EV. So these are relying on the measurements of these X-ray binaries, and some people don't trust these at the 100% level because they rely on a lot of modeling, but by taking them at face value, they go up to about 10 to minus 11 EV. So we want to go to higher frequencies than that to look for new parameter space. It's still interesting to look in this range to double check these bounds, but it's especially interesting to go to higher frequencies. The other point is that the axion, the axion mass is related to where it's a pseudo-Goldstone boson, and it's the symmetry of is from which the pseudo-Goldstone boson is produced is given by is broken at this high scale corresponding to Fa. And either in particle physics constructions where you have grand unification and lots of extra U1s showing up at this scale, that's one natural place where these symmetries could break. Or there's also string theoretic constructions where the scale of the axion, the Fa scale, is given by the string scale suppressed by some factor of order 100 or 200, and so that again points to the grand unification scale. So this is a kind of an interesting place to look theoretically as well.
Okay, thank you.
Nancy, go ahead.
Hi, Masha. Good to see you again. I have a question that might be unfair and might not be up your alley, but please feel free to shut me up if that's the case. What I was curious about when I was seeing your exclusion plots in mass and spin parameter space is when we are creating these black holes, what is the initial spin distribution that they get created with, or do we have any idea about that?
Yeah, that's a great question, and it is not up my alley, but it's not, to be honest, it's not up anyone's alley. Unfortunately, we've tried to talk to many people about this, and it's a very unknown parameter. So there's a few inputs that we do have. So there's data, which is that we have some of these black holes that we measure in X-ray binaries are rapidly rotating, and from the lifetimes of these binaries, we also know that they didn't have enough time to be spun up by accretion, so these are likely the spins that they were born with. Also, we know from mergers, of course, you capture lots of angular momentum, and then you can get a high spin. In supernova, there's some data, so that's evidence that some black holes are formed with high spin. There's also evidence that, say, neutron stars are born with pretty low spin, so we can measure the rotation of pulsars, and if we translate that into the equivalent rotation that the black holes would have if they were a bit heavier and collapsed to a black hole rather than a neutron star, then you would predict quite low spins, so around 0.1 or even lower. So there's likely at least two kinds of populations depending on the initial conditions of what's happening. We also know that there are some very highly rotating solar mass black holes because we see some GRBs with jets coming out that correspond to high spins. But in terms of quantitatively giving you a distribution, unfortunately, we don't have a good answer to that. And that's something that, if anyone has ideas on how to observe isolated black holes in the Milky Way and measure their spins, that will give us a lot of nice information for predicting these a bit more accurately. But right now we don't have that.
Yeah, thank you.
All right, so very interesting discussion. So we need to move on.